Today we are walking through the paper titled OPRD on Policy Representation Distillation.
Could you start from the problem this paper is trying to solve, huh?
The paper studies how to distill a strong reasoning language model into a smaller student while the student trains on its own generated solutions. Existing on policy distillation mainly compares the teacher and student after the language model head by matching next known probabilities. That output-only design leads to concrete problems. A single sample token gives a noisy estimate of the teacher-student gap, while full vocabulary or top key matching becomes expensive for long responses and large vocabularies.
So the older method either see too little signal or pay too much to see more?
Exactly. Sample token OPD is cheap, but its gradient behaves like a score function estimator and can keep noisy directions late in training. Full vocabulary OPD is dense, but storing a batch by time by vocabulary log its tensor is the wrong shape for long chain of thought training.
What does OPRD change in the supervision path?
OPRD moves the comparison before the language model head. The student and frozen teacher both process the same on policy rollout, and the loss aligns their intermediate hidden states across selected layers and positions. The architecture picture is the key. OPD extracts supervision at the output probabilities. OPRD taps the internal representations, so the teacher provides layered structure instead of acting only as a probability oracle.
When you say hidden states, what is being matched?
For each chosen layer and response position, OPRD takes the student's hidden vector and pulls it toward the teacher's hidden vector with a masked squared error loss in their main setting. Here is the paper's loss in compact form. It averages the squared distance between student hidden states H theta and frozen teacher hidden states HD over selected layers and masked response positions.
Why focus on the end of the response instead of every token equally?
The mechanistic analysis finds that early response positions are already close between student and teacher, while the end of the response has the larger representation gap, so the last token budget concentrates supervision where the student still diverges. The theory gives two reasons this can help. First, OPRD avoids per token sampling variance because the hidden vectors are deterministic once the rollout prefix is fixed. Second, the language model head can hide information, so output probabilities do not contain every useful internal direction.
How did they test whether this improves reasoning, not just the hidden state loss?
They train from an R1 distill 1.5B student against the just A or L1.5B teacher. Prompts come from DAPO Mass 17K. Each prompt samples the student responses, and all methods use the same rollouts: teacher forward pass, optimizer schedule, and 500 training steps. For evaluation, that means each problem gets 16 sampled solutions, and the score is the average exact match accuracy after extracting the boxed final answer.
What is the headline result on those benchmarks?
OPRD reaches 49.8 on A, IME24, 34.6 on A, IME25, and 79.1 on AIMO. Those scores are only 1.0, 1.0, and 0 points below the teacher, while the output stays so PD baselines plateaus several points lower. The result pattern matters as much as the final table. Across the three math benchmarks, OPRD keeps climbing toward the teacher level, while OPD top 1 and OPD top 16 flatten or oscillate late in training.
So it improves accuracy, but does it also change how the student reasons?
Yes. The response length analysis shows OPRD converging to about 5,700 tokens per response, while OPD top 1 and top 16 sit around 7,000 tokens. The student is not just writing longer solutions to compensate. It reaches better answers with shorter reasoning chains.
How do they know the representation objective itself is really being optimized?
They track representation cosine similarity on the supervised positions. That curve rises sharply early and continues drifting upward, so the downstream accuracy gains line up with the exact hidden state quantity OPRD trains. The cost result is also concrete. With the same 500-step schedule, OPRD finishes in 563 minutes, compared with 813 minutes for OPD top 1 and 812 minutes for OPD top 16. The reason is that OPRD avoids materializing the large vocabulary logit loss path.
And the memory reduction comes from not storing all those output logits?
Right. The actor update transient memory is lower because the hidden state loss bypasses the batch by time by vocabulary tensor. Against OPD top 16, the paper reports a 54% peak memory reduction, while also improving AIME 24 by 2.7 points. The strongest limitation is important too. OPRD compares hidden states, so it currently assumes the teacher and student share the same architecture. The authors say cross architecture hidden states are nearly orthogonal, and suggest learned projections or contrastive objectives as future directions.
So the takeaway is not just better scores, but a different place to distill from?
That is the paper's main message. Treating the teacher as a source of layered internal computation gives the student an end-to-end more stable training signal than output probabilities alone. If you remember one thing, remember this. OPRD keeps the on-policy benefit of training on student-generated trajectories, but moves supervision into hidden state space, where the teacher can provide lower variance guidance. That is it for this paper.